The title of this presentation is the use of PSPME for particle sampling of surfaces. And that's what we're going to do in the laboratory later this morning and part of the afternoon is we're going to do several exercises on removing particles from surfaces, which is primarily the way that illicit substances are detected in terms of the trace amounts. So the outline for this talk, we're going to talk about the principles of contact sampling. So far, the PSPME applications we did in the laboratory yesterday have been non-contact. Okay, so we've been sampling volatiles, either static or dynamic, non-contact. And there's a lot of interest in non-contact sampling, but primarily what's done currently out in the field is contact sampling. So we felt we needed to cover this. And the other thing you heard from Patty earlier this morning was that the substrate mattered quite a bit. So the force for lifting particles did not matter as much as the composition, the texture of the substrate. So there's been a lot of work, people developing different materials for removing particles. So now we have the ability to do non-contact sampling with PSPME and the possibility for particle removal using contact sampling. So we're going to use PSPME in the laboratory for that function. So we're actually going to cover particle sampling of surfaces, and then we're going to talk about alternative sampling modalities besides static headspace volatiles and dynamic volatile sampling, and besides direct contact sampling of surfaces. There are others, and we'll cover a few of those, and that'll lead us into some of the exercises that we'll cover later this morning, immediately after this presentation. So let's talk a little bit about the big picture. So you take 30,000-foot view of detection. Well, if you can't collect it, you can't detect it. So that's the first step. And if you go back even further, if the sample's not there, then you can't collect it. So first, the canine handler yesterday said the odor has to be available in order to be able to detect it. If it's there, then the canine can detect it. Well, same thing with particles. They have to be there, number one, and we have to collect it from wherever they are. So unlike volatiles, if you have a scent source in the corner of a room and you've got good circulation going on, well, the dog will eventually be exposed to some of those compounds, even though they're in minute quantities. They'll get to the dog's nose. That's different with particles. You actually have to swab or swipe the area where the particles are present. So you have to collect them, and then you have to expose them to the instrument. So we go from, we would like to do is improve this front end, which is collection, sampling, because if we do a good job here, we can enhance our ability to detect it. We enhance the sensitivity, we might even enhance the selectivity. That means we don't want to collect all those dust particles that are not going to lead to a detection and may even overload the instrument and interfere with the particles we want to detect. So we want to collect in the right spots. This is applicable to many different systems. And if you look at the big picture, for odors as well as for surfaces, we want to sample large volumes. When you have a swab, when you're just picking up particles off a surface, it's very difficult to do a whole table or a whole bag. So you're going to have to limit yourself to where you're going to collect. But ideally, you want to collect from high volumes. That's the first step. You have to get the particles into your system somehow. Then what we do is SPME is selective pre-concentration. We're going to concentrate those odors that are going to be important for us to detect. Part particle swabbing is similar to that. The instrumentation, IMS, provides a separation. So we'll get peaks at different migration times that will separate the components so that we can then detect them. And the numbers that you quoted this morning, those times are indicative of different compounds. Okay. Then we have a detector that's very sensitive, an IMS. We have an exquisitely sensitive detector, less than a nanogram of mass of material can be detected. Now then, after you have a signal from the instrument, you have to interpret that signal. We could automate some of that and turn it into a green light, red light situation. That's the analysis and the fusion, and then that goes to the decision maker. What happens next? What's the policy when you have this green light, red light? What does it mean? Do you go back and do some more work? Normally that's the analytical process, is a feedback loop. Once you have a signal, go back and take more sample, for example, do further investigation. So that's what the big picture. But you need to get the sample, otherwise it's not going to work. So there's been a lot of work here. There's been a lot of work here in the amount of force and the way that people remove samples from surfaces. And here's a little cartoon of having particles on surfaces. You get the particles onto the substrate, and Patty already said that the composition of the substrate plays an important role in how well you remove the particles. Okay, so we're talking about particles, but we're also interested in these volatiles. So PSPME offers the opportunity to do both. We have a mechanical removal of these particles onto the surface, and Patty's already talked about the particle sampling using surface wipes of different composition, different material, and she said the material is more significant than the pressure. Now, to assist us with training and evaluating particle sampling systems, NIST came up with a standard reference material which is 2905. 2905 can be purchased from NIST. It contains approximately 0.1% RDX and 0.01% TNT, and also has some HMX composition, and it simulates the composition of C4. And these are micron-sized particles. You cannot see the actual particles. And they come in a little vial, and I'll show you what it looks like. And they make them so that it simulates explosive particles. Explosive particles stick to surfaces, and that's an advantage. So if you have a bomb maker that is handling the explosive device and then packaging it, well, the explosives will get onto their fingers and then secondary transfer from the fingers onto the outside packaging. We're going to simulate some of that and then try to remove particles after simulated handling of explosives. So the reason why this standard reference material was created, 2905, was to evaluate the performance of these TEDs, these trace explosive detectors, for both calibration, detection, collection efficiency, and allowing people to make purchasing decisions looking at a standard reference material, doing the same thing with the same material with a lot of different instruments, and as well as developing standard operating procedures for collecting particles. So here's what it looks like. Under regular fluorescent lighting, you take a picture. This is what the little vial looks like. You see it's 2905. Trace particles. It's got 0.1% TNT. If you irradiate it with blue light, so it's got a wavelength of 420 to 470 nanometers, this blue light, this is what it looks like if you take a picture under blue light irradiation. If you look at the container through amber lenses, the orange lenses, then it looks like this. And if you combine irradiation of blue light and looking at it through amber lenses, which is what you're going to do, you get what we call fluorescence. So that combination of adding the amber lens increases the contrast, so you're able to see the fluorescence better. So if you irradiate it with blue light, we have some blue light, we have some amber lenses for each of you, we're going to see this fluorescence, bright light being emitted, which is a different wavelength than the light that's being used to irradiate the sample. That's the definition of fluorescence. Okay, we have a different light. This light happens to be yellow light, which is 589 nanometers. So it's a sodium line. And that's what you see. The eye perceives this particular wavelength really well, so that's by design. So what if we take a little drop of these particles and put it onto a surface? It's going to look something like this. These particles are microscopic, but you can see a bunch of them agglomerated together. If you disturb that drop with your finger, you're going to distribute it on a surface. We're going to try to visualize these in the laboratory. Normally, you want to do this under dark lighting conditions. Now, this is not something that you do in the field as a trace detector exercise. We want to do this to kind of illustrate the steps in capabilities for collecting particles. So we're going to deposit some particles. You can't see them unless you use UV irradiation, amber light visualization. It's the only way to see them. So we're going to ask you to collect the particles with the PSPME swab with and without this aid of visualization. See how you do. Okay, so we have some exercises planned for you. And I'm going to show a video right now on how ETDs are normally used for collecting particles off of people's hands, for example. This one doesn't have any volume, but you can see that we're swabbing the surface across the hands, trying to get as much surface area as possible with the swab. And then you can't see the reading here, but that's a negative. And this person is allowed to go through. Very, very quick, fairly straightforward. And maybe some of you have had that happen to you at a airport or some other point of entry. So that's how they're trained to use this. Now, there are other ways to do particle sampling that involves no contact. And I'll show you one way here is to produce airflow, high flow of air onto a surface, disturbing that surface, and then sucking in any kind of particles that are coming off the surface. So this is called a vortex, a mini tornado that's created onto the surface. Then the particles are sucked into the IMS and then ionized and detected as normal by the IMS. So this is instead of just normal air sampling like what we're doing, dynamic, a low volume, this is fairly high volume of air, plus they are disturbing the surface. The reason for disturbing the surface is to dislodge these sticky particles. Okay? And we no longer use these at airports, but in the past we've had these non-contact particle sampling alternatives where the air puffers, the puffs of air dislodge the particles trapped on hair, body, clothing, and we also have a video here. Somebody goes into this device, the air puffers are on, dislodging the particles, and then the particles are sucked up at very high volume onto an IMS. So there are alternatives to non-contact sampling. We want to sample simultaneously volatiles and particles. We want to get everything that's going to be relevant to us, while at the same time allowing any kind of interference, any kind of material that's not related to illicit substances go through. So the ideal material will be one that collects the particles we want, collects the volatiles we want, and lets through and does not collect the sample. So we're not there yet. This material does not exist. Okay, but there's an awful lot of work being devoted to this ideal material, so that then we can introduce it into an instrument. And what's the instrument of the future? Probably mass spectrometry. Probably mass spectrometry. So we got to get ready for great collection technique. That's where a lot of research is being spent there. But also unambiguous identification of compounds in the field quickly, without the need for a GC separation that takes 15 minutes. We've got to do this in seconds. So that's the future. We think PSPME has a role in there somewhere. So we're going to apply PSPME for particle sampling. We have other substrates that are provided by the manufacturers of the IMS instruments right now for particle sampling. You'll have an opportunity to use those. And then we're going to give you an exercise, a series of exercises for both surface sampling in the laboratory, and then we're going to take you out to the warehouse where we have some vehicles where you're going to be doing some surface sampling of the vehicle. And here's where we want you to focus: the steering wheel, the door handle, and the gear shift. Why? That's where the hands are. That's where the hands go. So if you've got secondary transfer from somebody who's just handled some illicit material, they're going to transfer that with their hands to the door handle, the steering wheel, the gear shift. Okay, so that's where the focus should be. There is a handout for this exercise. Before we get up and move to the laboratory, I want you to take a few minutes and read that. And then we can proceed. So in summary, particle sampling has these advantages: low cost. These materials are fairly inexpensive, very easy, very fast. They're designed to use with existing IMS systems. And because of this secondary transfer, they're an indication of relatively recent contact with material, which is a big advantage and plays into your policies as to what to do next when you do see a positive response. Here's a interesting paper by Michael Verkuterin at NIST, who has been working for several years now on removing particles using swipe sampling. And I recommend that if you're interested in measurement science and technology. Are there any questions about particle sampling before we move to the lab? No? All right. Thank you.